Right. So first of all, today I'd like to start with the introduction of the subject. Then we'll move to the objectives of this project. Then we will discover the simulation software developed in this framework, and we'll go through the results of its numerical validation. Then we will consider the automated peen forming workflow, and okay. Right. So we'll consider the simulation software, the results of its numerical validation. Then we'll go through the automated peen forming workflow, which is also one of our main achievements. We'll look through our experimental results, and we will conclude with recommendation for the future work. Shot peen forming is used in aerospace industry to shape large panels requiring slight curvatures, such as airplane wing skins, tank bulkheads of space missiles, and it is also used to correct distortion of the fuselage components. The process consists in projecting a large number of tiny particles towards the surface of the component. Each particle acts as a hammer, producing local plastic deformation. So if a certain zone of the component undergoes millions of impacts, then the whole upper layer in this zone becomes plastically deformed. Mechanically, this is equivalent to stretching of the upper layer of material that leads to bending and stretching of the whole component. In industry, peen forming is applied either automatically or manually. In case of the automated process that we see on the left, the process is executed in a closed compartment, and there is a robotic arm that follows predefined programmed trajectories and projects the particles at the same time. In case of the manual operation, there is literally the operator who is holding the nozzle, and then the particles that are reflected from the surface are immediately evacuated using a vacuum surrounding the nozzle. The automated process is more precise, more repeatable, and it is even safer because in general, peen forming is a very dusty and noisy process. However, its disadvantage is a long programming phase if it has to be done manually, because one has to literally program the trajectories coordinate by coordinate to make the robotic arm move. And this is one of the reasons why the manual process is still applied nowadays. Namely, the market does not propose a publicly accessible and a reliable simulation software. And this is why development of a new peen forming procedure for a new component is a craft, trial and error process. And of course, it is faster and cheaper to execute it manually than to reprogram the robot for each new trial. Talking about the peen forming simulation, the engineers here face two types of problems. The first one is the forward problem. It means determining the final shape of the component, providing with its initial shape and the peening pattern. This peening pattern is essentially a map of the treated segments and of the intensities applied to each segment. So numerical resolution of this problem might be useful to rapidly simulate corrections introduced in an already existing forming procedure. But in order to define a new peen forming procedure, we have to numerically solve the inverse problem, which means defining the peening pattern as a function of the initial shape of the component and the final shape that we want to have. And there is a couple of practical limitations imposed on the peening pattern. Namely, it must consist of segments treated uniformly, because the shot peening equipment is not able to gradually vary the intensity over the component. And also, the maximal intensity is limited by the equipment capacity. With this, let's move to the objectives. So, the general objective of this project was to develop all instruments and techniques that are necessary for an automated peen forming process. Namely, the first objective was to develop the inverse problem solver, which would prescribe the peening pattern as a function of the target shape. The second objective was to develop a segmentation strategy which would apply these practical constraints imposed by the equipment on the peening pattern and make it actually applicable in practice. And this segmentation strategy is supposed to work either with fixed peening regimes, or it should also propose optimal peening regimes by itself. So when we work with fixed regimes, it means that the segmentation algorithm only computes the segments and assigns a certain peening regime to a segment. And when it is able to vary the peening regime, it means that it also varies the intensity. Well, it freely varies the intensity assigned to each segment. And the third objective was to develop an automated peen forming workflow, which would actually allow to apply all these this pattern prescribed by the simulation software in practice. So, namely, the workflow would include calibration of the software, automated programming of the peening robot as a function of the peening pattern, and estimation of the forming error. With this, let's move to the simulation software, our first objective. First of all, I'd like to dive a little deeper into the physics of the process. So the through thickness profile of the plastic strain induced by peen forming is non-uniform, as we can see here. So to accurately simulate this process, we would have to split the plate into a very large number of thin layers and to make them expand following this plastic strain profile, following this through thickness profile. But there is a technique that allows to reduce the number of variables in this problem. Namely, the plate can be represented as a bilayer where the upper layer undergoes a uniform stretching and the lower layer undergoes uniform contraction. So a plate loaded in this idealized way as a bilayer deforms into the same final shape as the one loaded with the original profile. However, it should be mentioned that the residual stresses induced in the structures loaded in these two different ways are different also. But the main concern of peen forming is the form of a component, its shape. So in our software, we adopt this idealized formulation in order to reduce the number of variables. And also this relation between the actual peening parameters or peening regimes and the amount of plastic stretching, epsilon top and epsilon bottom, can be determined experimentally. So let's have a look on how we solve the forward problem and how we formulate it. So the initial shape of the component is always flat. And physically, it is a flat bilayer plate, but numerically, it is a surface meshed with triangular shell finite elements. Then, in order to load the plate, we assign to each element a certain amount of plastic stretching or contraction to its upper and lower layers. With this, well, in fact, this general approach of loading the component with a non-elastic strain assigned to its structure is called the eigenstrain approach. And this non-elastic strain is the eigenstrain. So in our case, epsilon top and epsilon bottom fit the definition of eigenstrains. So we'll load the component element-wise with these eigenstrains, and in this way, we can actually draw many different peening patterns. For example, as we see here, we see 4 local load cases in this pattern. For example, the blue elements correspond to stretching of the top layer, which essentially means treatment from the top side. The red elements correspond to contraction of the top layer, which means treatment from the bottom side. The lighter blue elements stand for treatment from both sides, so that the induced eigenstrain is a superposition of the eigenstrain induced by treatment from both sides. And the gray elements stand for the absence of treatment. So when the plate is loaded, we minimize its global elastic energy functional with respect to the coordinates of vertices in the mesh and with respect to the normal vectors. Numerically, we do this. We use the LBFGS algorithm in order to perform this large-scale minimization. So here in the bottom, we can see a couple of examples of the plates deforming under various peening patterns. Actually, I even have one of them here today. So you see this kind of checkerboard pattern, which is deformed in a very beautiful wavy shape from both sides. You can see here. Our programming code that solves this problem is implemented in C++ programming language. The computation time is from 7 to 15 seconds for a plate of 1,600 elements, for example. And the code was developed in collaboration with Professor Van Ries from the MIT. Thank you, Wim. So this forward problem solver is majorly the achievement of Wim Van Ries. Next, talking about the inverse problem solver, which was one of our main objectives in this project. So the input for this problem is the initial shape of the component and the target shape that we want to achieve. And our algorithm for resolution of this problem is iterative. So first of all, it makes an initial guess on the eigenstrain pattern based on the target local curvatures that are present in the target shape. Then it solves the forward problem and computes what we call a current shape. This current shape is somehow similar to the target, but does not reproduce it exactly. So the algorithm essentially evaluates the discrepancy between the current and the target shape. This discrepancy is evaluated in terms of the Hausdorff distance, which is in fact the maximal local discrepancy if we superimpose the two plates as well as possible. So it is one number. If the Hausdorff distance is higher than a certain predefined threshold, then the algorithm recomputes the eigenstrain pattern element-wise based on comparison of the local areas and curvatures of the target and the current shapes. So this recomputation phase is done almost instantly because it is done on a local scale and it involves simple arithmetic operations, only essentially multiplication and subtraction. So the only phase of this iterative process that actually takes a considerable amount of time is the forward problem resolution, because we have to minimize the global elastic energy. For this reason, the time needed for the inverse problem resolution essentially equals the number of iterations multiplied by the time needed for the forward problem resolution. So when the Hausdorff distance is finally lower than the predefined threshold, we exit the iteration loop and we obtain what we call a free pattern. So let's have a look at this. So in this context, we'll talk about our segmentation strategy. Let us consider a somehow simpler target shape, a nice wavy target shape that we see here. Our iterative algorithm provides us with a free pattern that we see in the center. There is a certain amount of eigenstrain prescribed to each element, but as we can see on this picture, the colors of this pattern are somewhat non-uniform, meaning that each element is prescribed with a slightly different eigenstrain. So, and the eigenstrain actually corresponds to real peening parameters. And of course, we are not able to vary the peening parameters so often throughout the shaping process. So that's why we need to do the segmentation. And to do this, we project each element in the peening pattern as a point on a plane with coordinates epsilon top and epsilon bottom, which denote the eigenstrain prescribed to this element by the inverse problem solver. And since this point, the problem becomes purely mathematical, because our segmentation algorithm has to split this set of points into clusters and to compute an optimal centroid for each cluster. Or in other words, the mean point for each cluster. And then when the centroids are defined, we assign each element in the peening pattern with the eigenstrain corresponding to the centroid of its cluster. So we kind of homogenize the eigenstrain inside each cluster. And in this way, as we see here on the bottom, the pattern becomes very nice and uniform. It is composed of strictly divided segments, which finally can be reproduced in practice. And the segmentation strategy works for two cases. So first of all, we have predefined peening regimes. In this case, it means that we have fixed centroids. We cannot move the centroids because the eigenstrain that we can use is already predefined. So the problem in this case is very simple. We just attribute the points to the closest centroid in terms of the squared Euclidean distance. But in the second case, when we have to define the optimal peening regimes, or in other words, we have to find the optimal positions of the centroids, we use a modified k-means algorithm. First of all, let's consider how does this simple k-means algorithm work. So first of all, the algorithm initializes the centroids in random positions. The centroids here on the left are marked with these colored circles. And then it assigns the points to the centroids based on the nearest, based on the squared Euclidean distance. So it assigns the points to the nearest centroid. Afterwards, it recomputes the centroids as the mean of all points in the cluster. Then once again, it reassigns the points, recomputes the centroids, and iterates until stabilization of the centroids. But this strategy doesn't work in the peen forming case. Why is that? Because in our case, the centroids are interconnected. We cannot move them freely. Well, indeed, the treatment can be applied from both sides, and both treatments influence the eigenstrain induced on both layers. So we have only two layers, and they're influenced by both eigenstrains. So each centroid is a superposition of two peening regimes. So for example, if we have n peening regimes, it means that we have n+1 squared centroids. Why +1? Because the absence of treatment, no peening, is essentially treated as an additional peening regime. So here in the center, in the bottom center, we can see an example of the centroids, of 4 centroids that are generated by only one peening regime. So in practice, our objective is to alter the peening regime, not the centroids. And this is what we do on the third stage of the algorithm. So we take into account the present partition of the points, then we recompute the peening regimes, and only after this, we recompute the peening centroids, the cluster centroids, as all possible combinations of these new peening regimes. Good. Let's move to the numerical validation. So our strategy for the numerical validation was the following. We fixed an initial shape of the component as a square plate 1 meter by 1 meter. Then we assigned it with a random thickness, random Poisson's ratio, and we generated a random peening pattern. In this way, we generated 100 different test cases. Then we solved the forward problem for each test case, and in this way, we had 100 random target shapes. And we used these target shapes to validate the inverse problem solver. So the objective of the inverse problem solver was to reproduce the random pattern that was generated initially. And to quantify the error, we solved the forward problem once again for the free pattern and for the clustered pattern, and we measured the Hausdorff distance between those two final shapes and the target shapes that they were supposed to reproduce. We can see the results here. So first of all, let's look to the left and consider the free pattern, the error with the free pattern. So what we can conclude here. the error lies in the range of 4 millimeters, which we consider is a very satisfying result, given that the plates were 1 meter by 1 meter. And also, for more than 80% of cases, the error is lower than 1 millimeter. Then, if we look to the right, we see that the clustering algorithm essentially increases the error a little bit. Well, indeed, the clustering algorithm does not take into account its influence on the final shape, right? So, for example, in this case, if we look onto an example of the clustered pattern, there is this orange zone. This was not correctly classified with respect to the random pattern that was supposed to be reproduced. However, this influence is very mild, because the error stays in the range of 4 millimeters, and it even stays in the range of 1 millimeter for more than 70 cases out of 100. With this, let's move to the automated pin forming workflow. Here we have a little overview of the workflow. We start with the target shape that we want to obtain. Then we load it to the simulation software. The simulation software provides us with the peening pattern. And next, this peening pattern is loaded to what we call the translation software. This translation software essentially transforms the peening pattern into the trajectories for the robotic arm. And it also assigns the real peening parameters as the function of eigenstrength prescribed to the peening pattern. So the output of this translation software is a programming code which can be directly loaded to the peening machine, to the peening robot. So the only manual thing that has to be done is just to press the start button. The treatment happens in a closed compartment, as I've already said, and the component is installed. It is actually clamped along its perimeter with a removable jig. So when the treatment is finished, the component is removed from the jig and scanned with a 3D scanner. Then we numerically superimpose the target shape and this numerical model of the final shape, and we obtain what the error map, showing all these local discrepancies between the two shapes. And the Hausdorff distance actually is the maximal local discrepancy, which is on this example on the left bottom corner. This dark red color stands for the biggest error, the Hausdorff distance. And here we can see the automated pin forming process in action. So there is a robotic arm moving according to the trajectories. Then the panel turns by 180 degrees, and the robotic arm continues treating on another side. And here on the right, we see some examples of the treated components, but of course you can see them in large numbers here in this room today. I will show them later. So these lighter zones, they have lighter color. They essentially correspond to the treated segments. Now, talking about the calibration of our automated workflow, which is essential to make everything work. So first stage of the calibration is to define what is the offset between the parallel path of the peening nozzle. And to do this, we take a flat dummy specimen which has a very clean reflective surface, and we treat it with one passage of the peening nozzle. Then we scan it with a simple document scanner. We perform the image analysis, and in this way we determine the distribution of particles in the shot stream along the width of the shot stream actually. And after this, we define the maximal distance between the parallel shot streams that provides us with a uniform coverage. So we essentially superimpose these Gaussian curves in the way that their superposition gives a straight line, so uniform coverage. Another step of the calibration, which is maybe the principal step, is to establish this relation between the actual peening parameters and the eigenstrengths, epsilon top and epsilon bottom. So to do this, we fix the peening parameters and we treat a set of small coupons uniformly. These coupons, they are made of the same material and have the same thickness as the panels that are supposed to be treated afterwards. And then we measure the deflection of these coupons, and then we use our simulation software in order to adjust the eigenstrains so that the simulated deflection fits the measured one. And the third calibration step is characterization of the material anisotropy of the aluminum plates. So where does it come from? It comes from the rolling process, which is used to fabricate the plates. In fact, the material properties of the plates are slightly different in the rolling and in the transversal directions. So for this reason, even a perfectly symmetrical impact induces slightly different eigenstrains in these two directions. But this proportion varies from one type of aluminum to another. So it has to be quantified for each particular component. And to quantify it, we perform what we call the wave experiment. So what we do is we treat two plates using a wave pattern, which looks like this: treatment of one half from one side and of another half from another side. This provides us with a beautiful wavy shape like this. And then, so we treat two panels, at least two panels in this fashion, and on one of them, the wave is induced along the rolling direction, and on another plate, the wave is induced in the transversal direction. And this is essentially the objective of the wave pattern, to orient the deformation of the component. Then we measure the curvatures of plates, of these two plates. They are different due to the plastic strain anisotropy. And then once again, we use the simulation software that adjusts the coefficient of the eigenstrain anisotropy according to the experimental results, so that the experimental results correspond to the simulated ones. Now let's move to the experimental validation of everything that we have done so far. So first of all, we decided to validate the forward problem solver, because it is essentially the thing that binds all the inverse problem solver as well, right? So we took 9 panels, 32 by 32 centimeters, 2 millimeters thick, made of aluminum 6061 T6, and we generated 9 random peening patterns for these plates. In fact, each pattern implied only one peening regime, but the peening regime was applied from both sides. And the objective of this validation was to compare the simulated results with the practically achieved shapes. We quantified the error with the Hausdorff distance, which was non-dimensionalized with the total deflection of the target shape, So as we can see here in the bottom left, this dimensionless error was quite tangible, from 8 to 28.5%. But partially, this was our point during this validation, because we fixed the maximal possible intensity in order to deform the plates as much as possible and to trigger all sources of error that can appear. And then the sources of error were qualified and quantified. So the first source of error is what we call the effect of pre-stress. So in fact, when we were treating these plates, the pattern was first completely reproduced from one side, then the panel was turned, and the pattern was completely reproduced from another side. But the problem is that when we actually turned to treat the second side, the plate was already bent a little bit towards the first side. And this effect decreased the eigenstrains induced on the second side with respect to the simulated ones. What we recommend to do in future is to constantly alternate the treated sides during treatment. The second source of error were the forces and moments coming from the clumping support. So, given that the intensity of peening was very high, the panels were undergoing a tangible expansion. And since they were firmly clamped by the support, there was a strong contracting force acting from the support, which once again altered the eigenstrain with respect to the simulated one. So what we recommend to do in future is to let the plate at least expand freely while keeping it fixed. This will at least remove this contracting force. There will be some bending moment present, but we expect that its influence is lower than the contracting force. And the third source of error was our shot stream, which was simply a little too wide to reproduce the small particularities of the peening pattern. So in future, we recommend to use a little bit a thinner shot stream that would be more precise. Now, I forgot to mention actually that we have a real example of the freeform surface, which is presented here in the bottom on the slide here in the room today. So maybe if you're interested, you can have a look on how does it actually looks like. There are only 4 panels here because a surface of 9 panels would be a little bit too big. Then we decided to validate our inverse problem solver. So in this case, the objective was quite simple. We had a numerical model of an airplane wing skin, and the objective was to shape its upper and lower skins. Yeah, its upper and lower skins of the wing. So we generated the 2 peening patterns, which implied multiple peening regimes this time, and we applied it on the plates of the same size, 32 by 32 centimeters, but this time made of aluminum 2024 Q3. And then we compared the developed shapes with the results of the simulation. In this case, the error was a little bit lower than during the forward problem validation because the applied intensities were lower. And we suppose that this error is provoked by the reasons that were mentioned above, by the same reasons, by this kind of inconsistency between the simulated conditions and the real peening conditions. And we don't blame it on the inverse problem solver because it was already validated numerically and showed very good results. So we can see this nice wing skin here today. So after installation, its upper and lower skins perfectly corresponded to the simulated shape, but of course there is some force applied by the binding bolts, but this is often the case in industry. So after installations, the plates perfectly fit the simulated shapes. And these black parts here were printed in 3D from plastic, just to make this demonstrated. Finally, to conclude, I would like to say that we have developed the forward problem solver, the inverse problem solver, and we have developed the segmentation strategy. All these 3 components were validated either numerically or experimentally, and the inverse problem solver was validated in both ways. We have also developed the automated pin forming workflow, which was applied during our experimental campaign. So in future, we would like to recommend to dedicate the work to decreasing of the simulation error, of course. But the sources of error are defined and the avenues for their eliminations are proposed as well. So we hope that this will be done in the future. Another avenue for the future work would be to determine the peening induced stretching, because during our experimental campaign we were only determining the deflection of the coupons, but which is essentially related to their curvature. Okay, the deflection is related to the curvature, but it would be good to determine the stretching of the coupons provoked by the given treatment, which may be useful for some high precision applications. And also, maybe it would be possible to optimize our wave experiment so that smaller plates can be used for this, or maybe even smaller coupons, and this will save some material. Also, an important modification, well, an important improvement would be to include a possibility to simulate treatment of reinforced components, which are also sometimes shaped using sharp beamforming. And finally, our clustering method was not tested experimentally yet. So it would be good to do this. And in particular, it would be good to determine an algorithm for defining the peening regimes as a function of the prescribed eigenstrings. Because as for now, we were only doing it vice versa. We were fixing the peening regimes and defining the eigenstrings. But in this case, we have to find the peening parameters provided with the prescribed eigenstrings. And of course, we can do it by trial and error, but maybe there is a more optimal way to achieve this. Finally, I would like to thank everyone who was involved in this project. So I would like, of course, to express my sincere gratitude to my research supervisors, Frédéric Gosselin and Martin Lévesque. It was a great pleasure working with them. And honestly, they provided me with a lot of time, with a lot of help and support, with every support that I needed, actually. I never even asked anything. I was just always given. So it is very rare when people have such great relations with their supervisors at work as I do. I would also like to thank Professor Van Ries for accepting to collaborate with us on this project, for helping in organizing my internship at the MIT and for supervising this internship. This was a great experience that gave a great impetus to this project, and it was very interesting on a personal level. And also Professor Van Ries shared with us his numerical results that he had by that moment. In addition, I would like to thank Hongyam Yao for a lot of help that she provided for the organizational work and for helping in writing the articles. I would like to thank Pierre-Olivier Dubois from the CTA for developing this translation software. This software is his job. Was his work, sorry. Then I would like to thank Raphaël Paradis for designing and developing the removable jig for the plates. Nada Abbasi, who did all the manipulations related to fabrication of this demonstrator, wing skin demonstrator. Olivier Duchesne, who fabricated this exceptional front and rear components of the wing skin in 3D, who printed it in 3D. And Jovan Kostenov, who designed and fabricated these very nice supports for our freeform surface. And also on a personal level, I would like to thank Pierre Faucheur, who did not contribute to this project directly, but who provided me with a great mentoring and with a lot of help in the beginning. So on this soulful note, I would like to end my presentation, and I would be happy to undergo a high-intensity treatment with a series of questions, possibly in French. Thank you for your attention.
Perfect. OK. Merci beaucoup, Vlad. Alors, je propose de commencer les questions des membres du jury. On commence par membre externe. Alors, professeur Roux. Après ça, professeur Martin. Étienne Martin.